Now what I'm going to do for this class of Math 1103, I'm going to produce these short, hopefully they're short, videotapes, place them on YouTube, and it will review the lesson that comes from the textbook, in this case page 7. It's something you could have done at home, but if you like to see it done, well, that's what this is. So for section 1.2, we're talking about symbols and sets of real numbers. Now, some of this you may know, because this is given in most algebra courses at the start. In advanced ones, they wouldn't do it because they assume you know it already. So the first set of numbers that we deal with are called natural numbers. And natural numbers are sometimes called counting numbers. It's numbers we use to count things. And the first number we use to count something is 1, then 2, and then 3. And this pattern continues, and these 3 dots reflect that pattern continuing, and the 3 dots are called an ellipsis. And this would go on to infinity, which is this symbol here, kind of like a sideward 8. Our next group of numbers is our whole numbers. Okay, what's the difference between natural numbers and whole numbers? Well, we've added a 0. In counting numbers, that set doesn't have a 0. But in whole numbers, it does. So 0, 1, 2, 3, and again, going up to infinity. And that's positive infinity. Now, we often think of the number line. We've used this a lot. When I started back in my high school days, we didn't talk about the number line, but as I taught math and other subjects, we used the number line. So the number line is a horizontal line on which we place the numbers and assign them value. Now, to graph the natural numbers on a number line, we do so by putting a dot on the number we're talking about. So if we're plotting 1, we put a dot there, 2, and we continue. Now, we don't have to go on to infinity, but we can show the ellipsis by just indicating that our arrow is, in a sense, our ellipsis, that it goes on to positive infinity. Well, that's the number line graph of natural numbers. Now, using that same graph, how do I reflect whole numbers? Well, just by adding another dot at 0. That is now the graph, the number line graph of whole numbers. All right, another point they ask us to cover here is symbols. And many of these you know, but just to review, the equal sign. That is, what's on this side is the same as what's on that side. That's equal. With a slash through it, does not equal. Now, these inequality signs, students tend to get mixed up, and I get mixed up every once in a while, but fortunately not too often. Again, the point of an inequality sign is toward the lesser. The open part is toward the greater. So if we're reading this from left to right, what's on this side is less than what's on that side. So this is a less than sign. Again, the open part is toward the greater. So this would be read from left to right, greater than. Now when they put a bar under it, it's read less than or equal. Less than or equal. Greater than or equal. And then how are these used? Well, it ties into the number line. If something is to the left on the number line, that is less than something to the right on the number line. 1 is less than 2. 4 is greater than 1. 1 is less than 5. So if we can imagine a number line, that helps us correctly put in the symbols here. So for our first example, and again, these are all worked out in your textbook, 2 is going to be less than 3. 7 is greater than 4. 72 is greater than 27. Now you're going to have an opportunity to do these in the practice, and then later the quiz me. And as you gain your mastery points, you're preparing for the test on Chapter 1. Now in example 2, they're asking, is something true or is it false? So we're saying 8 is greater than or equal to 8. As long as one part of it is true, then this is true. Now 8 is less than or equal to 8. Again, one part is true. 23 is less than or equal to 0. That's not true. That's false. 23 is greater or equal to 0. That is true. If these were the only sets of numbers we had, we'd find we couldn't get very far in math. So there are other sets of numbers. Another very common set are the integers. Now, what are the integers? Well, on our number line, you notice we stopped at 0. But there are integers to the other side of this, or numbers to the other side of this. -1, -2, -3, -4, -5, and again, so on and so forth. Now, how do we define the integers? Well, I've seen different ideas of this, and the one I think I like is if you have 1, which is a counting number and a whole number, does it have a number on the other side of 0 that when added to 1 makes a 0? And the answer is yes. We have a -1. That 1 and a -1 would be a 0. We say the -1 is the additive inverse of 1, or is its opposite. So whole numbers, or in this case counting numbers, have an opposite on the other side of 0, and we often think of this as to the left, and then this is to the right. And these numbers now, along with the counting numbers and their opposite, make up our next group of numbers that are called integers. So this is coming now from a negative infinity going to a positive infinity, and we use our ellipsis to indicate that pattern continued, and this is the way we show the set of integers. Now, are there other numbers on the number line? And the answer is yes. For instance, between 0 and 1, we have 1/2. And we also have, let's say, 1 1/3 there. Or let's just stick the 1/3 in here. Now, when we take the number 1/2, which is, let me just do that this way. If we convert 1/2 to a decimal, we get 0.5. If we convert 1/3 to a decimal, we get 0.3, and the 3's continue to repeat. So we just put a little repeating bar above the 3. Well, these whose decimal fractions, they're not a whole number, they're not an integer, but there's something in between, and whose decimal terminates like 1/2 does, or repeats like 1/3, these make up our next set of numbers called rational numbers. And you may have heard of another grouping of numbers that are the irrational numbers. Well, what are they? Well, if you go here, a little bit over perhaps, a little bit more, you get what is called the square root of 2. The square root of 2 is a number that's on the number line, but when we take the square root of 2 and convert it to a decimal fraction, it starts off 1.414, and it just continues on and does not terminate. Because theoretically, if you take this number and multiply it by itself, you're supposed to get a 2. Well, you never quite get a 2. You get a 1.9, and it never quite makes a 2. So we say those kinds of numbers that don't terminate or repeat in a pattern, but just continue on, those are the irrational numbers. And generally you can recognize an irrational number as a number under the radical sign. Now there are some exceptions. For instance, if you have a perfect square under the radical sign like 4, here it's telling you this is an operation sign. Take the square root of 4, which is 2. 2 is a natural number, a whole number, an integer, and it's rational, even though it's under the radical sign. But all the numbers that are not perfect squares, like the square root of 3, like the square root of 5, square root of 6, square root of 7, all of these numbers, they're not perfect squares, are irrational. Why? Because when you convert them to their decimal form, it doesn't terminate or repeat. Here it terminates, here it repeats, here it doesn't. Now another famous irrational number is the symbol pi. We often think of it as 3.14. But again, that's just approximation. It is an irrational number. Now we'll do some examples. All right, I'm going to skip example 3. It's just to put various English words into their mathematical symbols. So you can look at that yourself. But example 4 is how to write 72 below 0. That's the temperature. Well, in a case like this, below 0 refers to the left of 0, so that would be negative 72. Now, for example 5, they're asking us to look at this set of numbers and identify them as to, are they natural numbers, whole numbers, integers, rational, irrational, and then, by the way, all of the numbers on the number line make up the set of real numbers. So they're going to ask us, which do they belong to? Now again, until you try it and do it, you don't know if you've mastered that skill or not, but if you want to try it ahead of time, pause the tape. Otherwise, we're just going to go on. So, negative 2. Well, it would be, it's not a natural number, it's not a whole number, but it is an integer, it's rational, and it's a real number. In fact, all of these are real numbers. 0. Well, we see it's a whole number, it's not a natural number, it's an integer, and it's a rational number, and of course a real number. 1/4 is not a natural number, it's not a whole number, it's not an integer, but it's on the number line, and when we convert it to its decimal fraction, it's 0.25. So it's a rational number and a real number. You see, I left the L out of here. By the way, if you're one of my students and you see that I might make a little error, I usually give a bonus point. I'm not sure how I could do that, but I'll try to work out something. I'll bring it to my attention, and you get what is called a math star. That's symbolic right now, but just say, oh, you made a little error. I apologize for those. Okay, a negative 1.5. Now, it's not a natural number. It's not a whole number. Is a negative 1.5 an integer? No, because it's between a negative 1 and a negative 2. It's right there. So it is a rational number and a real number. Now 112, way out there, is a natural number, a whole number, an integer, and a rational number, and a real number. The only thing 112 isn't is irrational. Negative 3 is an integer, rational, and real. 11 is the same as this one. Everything but irrational. And then the only one that's irrational is this square root of 2, which we said approximates to something, but it doesn't terminate as a decimal. All right, going on to example 6, and remember all of this is included in your textbook, and you'll be having practice and then later quiz me's on it. They want us to put inequality signs in here. So -1 compared to 0. Well, there's -1, 0, it's to the left, so this will be less than. Now 7 as compared to 14 halves. Notice 14 halves can be simplified. 2 goes into 14 7 times. So that's going to be equal. Now let's put a -6 over here. -5 is what compared to -6? Well, notice -5 is to the right of -6. Anything to the right, we said, was greater. All right, taking us to our next item, and we're introducing a new symbol in math, and that is vertical lines around a particular term. These vertical lines indicate what is called absolute value. Now, what is the absolute value of anything? And the answer is its distance from 0. So how far is a -4 from 0? Well, we count. 1, 2, 3, 4. It's 4 counting units from 0. And remember, when we count, we're using positive numbers. So we then say that what is absolute value of anything that's found between these vertical lines? And the answer is it's always its positive value, because it's distance from 0, and those are counting, so those would be positive. So absolute value of 4 is 4. Absolute value of -5 is 5. And 0 is just 0. -1/2 is 1/2. And a 5.6 is 5.6. Absolute values are always its positive value. Now, every once in a while, they'll give you a little challenge. They'll say, they'll put a negative out in front of the absolute value. And then this comes out of the absolute sign as a +5, but then we apply the negative. So this would be a -5. We'll have some of those a little later. All right, going on now to the last example. We're asked to insert an inequality sign or an equal sign, less than, greater than, equal, into these 5 examples. Now, absolute value of 0 is 0. 0 is less than 2. The absolute value of -5 is 5. So 5 equals 5. The absolute value of -3 is 3. And again, you can write these out if you like. So this would be greater than. And 5 is less than 6. And again, this is a +7 is going to be greater than 6. All right, this completes our first topic on symbols, sets, and sets of real numbers. You have your practice, you have your quiz me's, and you should be reading over section 1.3 to help prepare for our next lesson.